For over a century, the world of physics has been founded upon a single, unwavering certainty: that nothing in the universe can travel faster than the speed of light. The equations of Albert Einstein seem to construct an impassable frontier, a cosmic speed limit that no technology or civilization could ever hope to surpass. This was not merely a technological challenge to be overcome, but a fundamental property of reality itself, woven into the very fabric of space and time. And yet, concealed within those same revolutionary equations lies something genuinely extraordinary. It is not a simple loophole that breaks the limit, but a much more perplexing idea: the suggestion that space-time itself could be manipulated, stretched, and compressed to carry a vessel across vast cosmic distances without ever violating the local speed of light. The implications are profound, but the constraints are so immense they make the original barrier seem almost trivial. What this exploration has revealed tells us something deep about the architecture of our universe. Join us on Calm Space as we delve into this mystery. It is a simple, declarative statement: you cannot travel faster than light. At first glance, this might sound like an engineering problem, a hurdle awaiting a more brilliant mind or a more powerful form of propulsion. After all, human history is filled with supposedly insurmountable barriers that eventually gave way to human innovation. We once believed the sound barrier was absolute, and that flight for objects heavier than air was a defiance of nature itself. So why is the speed of light any different? The answer is that this limit is not an obstacle standing in our way. It is a property embedded within the foundational structure of the cosmos. To truly grasp this, we must journey back to the year 1905, when a 26-year-old patent clerk named Albert Einstein quietly began to rewrite the laws of physics. Before Einstein, our understanding of motion was deceptively straightforward. If you were on a moving train and threw a ball forward, the ball's speed would simply add to the train's speed. It was a matter of basic arithmetic, a principle confirmed by everyday experience and perfectly described by Newtonian physics. However, a deep inconsistency was lurking within the equations of electromagnetism, which had been formulated decades earlier by James Clerk Maxwell. His work predicted that light moves at a constant speed of approximately 300,000 kilometers per second, regardless of the motion of its source or the person observing it. This prediction was deeply strange. In our world, if you drive toward an oncoming car, its approach seems faster. If you chase it, its relative speed decreases. Light, however, refused to follow these familiar rules. No matter how quickly you moved toward a beam of light, it would still approach you at the exact same speed. Experiments repeatedly confirmed this bizarre fact: the speed of light was an absolute constant. Faced with this paradox, Einstein proposed something truly radical. He suggested that instead of trying to alter Maxwell's equations, we should instead transform our fundamental understanding of space and time. If the speed of light must be the same for every single observer, then it must be space and time themselves that are flexible, adjusting as needed to preserve this universal constant. From this new perspective, distances must contract, time must slow down, and the very idea of two events happening simultaneously becomes relative to the observer. This revolutionary concept, known as special relativity, unveiled an astonishing truth. It showed that space and time are not independent, separate stages for the universe's events to play out on. Instead, they are intricately woven together into a single, four-dimensional fabric called spacetime. As you move through space, your own journey through time is altered. Consider the famous thought experiment involving two twins. One twin remains on Earth, while the other embarks on a journey aboard a high-speed spacecraft. Upon returning, the traveling twin, according to the principles of relativity, will have aged more slowly. When they are finally reunited, the spacefaring sibling is measurably younger. This is not a mere theoretical curiosity. It is a repeatedly verified fact of our universe. For example, atomic clocks flown on commercial jets tick at a slightly different rate than identical clocks left on the ground. In particle accelerators, subatomic particles are observed to exist for longer than their normal lifespan because, from their high-speed perspective, time itself has slowed down. As an object's velocity increases, this effect, known as time dilation, becomes more pronounced. At 90% of the speed of light, time for the traveler slows to about half the rate experienced by a stationary observer. At 99%, the effect is even more dramatic. As you push ever closer to that ultimate limit, time for the traveler nearly grinds to a halt relative to the outside universe. But as this happens, another, more formidable barrier emerges. The energy required for acceleration begins to skyrocket. As you accelerate an object, its kinetic energy increases. In the relativistic framework, energy and mass are two sides of the same coin, linked by Einstein's iconic equation, E equals mc squared. The more energy you pour into an object to accelerate it, the more its effective mass increases, making further acceleration progressively harder. This relationship is not a straight line. It is a curve that bends steeply upwards, much like trying to climb a mountain whose slope becomes vertical just before the summit. To reach the precise speed of light would demand an infinite amount of energy. Not just a vast or incomprehensible amount, but a true infinity, a quantity that simply does not exist in the physical world. This is the reason why the speed of light is not simply a difficult-to-reach milestone. For any object with mass, it is fundamentally unreachable. Even if you could somehow harness the energy of entire stars or galaxies for fuel, the mathematics of spacetime itself would still forbid you from crossing that boundary. The closer you get, the more the universe pushes back, as if the summit itself is receding with every step you take. But there is an even more profound and unsettling reason for this cosmic speed limit, one that is tied to the very logic of reality itself: causality. This is the principle that a cause must always precede its effect. A spark ignites a fire, a stone hits the water, and then ripples spread outward. This sequence feels absolute and non-negotiable. Relativity reveals that, while the perception of simultaneous events is not absolute, the fundamental order of cause and effect is preserved for all observers, as long as signals travel at or below the speed of light. If faster than light travel were possible, this logical structure would collapse entirely. In certain frames of reference, a signal sent faster than light could arrive at its destination before it was even transmitted. With the right configuration, you could receive a reply to a question you had not yet decided to ask. You could witness an effect and then travel back in time to prevent its cause. This creates intractable logical paradoxes, closed loops in time where events undermine their own existence. The speed of light, therefore, acts as a guardian, preserving the coherent flow of history. Imagine space-time as a grand architectural structure. In this framework, the speed of light is not merely a decorative rule painted on a wall. It is a primary, load-bearing beam supporting the entire edifice. If you were to remove it, the structure would warp and collapse in on itself. Relativity does not just say you are forbidden from going faster. It explains that doing so would shatter the very logic that holds our reality together. This is precisely why the barrier feels so absolute. Unlike the technological limits humanity has overcome before, this one is embedded in the geometry of the universe itself, arising from the fundamental way space and time are interlocked. A fundamental principle protects the consistency of physical law throughout the entire cosmos. For many decades, this core idea seemed absolute. Nothing can travel faster than light. This was not viewed as a simple limitation of our engineering or a temporary technological barrier, but rather as an intrinsic rule woven into the very fabric of the universe itself. And yet, the story does not conclude there. In the year 1915, Albert Einstein expanded upon his own groundbreaking work, revealing that space-time is not the rigid, unchanging stage it was long thought to be. He demonstrated that it can bend and curve in the presence of mass and energy. This profound insight opened a conceptual doorway that almost no one had anticipated. While objects are forbidden from exceeding the speed of light within the medium of spacetime, a new question naturally arose. What if the medium itself could be made to move? If special relativity constructed this seemingly impassable wall, then general relativity began to reveal the vast and unknown landscape that might just exist beyond it. In 1915, Albert Einstein once again transformed our view of the cosmos, this time by redefining not motion, but gravity itself. For centuries, gravity had been understood as an invisible force, a mysterious tether pulling objects toward one another across the vast void. An apple fell because the Earth tugged on it. Planets circled the Sun because of its immense gravitational pull. Einstein, however, offered a far more elegant and strange explanation. He proposed that gravity is not a force at all, but is instead a consequence of geometry. The presence of mass and energy warps the fabric of space-time, and objects simply travel along the contours created by this curvature. Imagine a heavy ball placed onto a stretched rubber sheet, causing a deep depression in the material. A smaller marble rolled nearby will appear to be pulled toward the ball, but it is actually just following the straightest possible path along the distorted surface. This is the very principle that governs the orbits of planets and holds entire galaxies together. Even light, which has no mass, must follow these curves as it travels near massive objects. And within this beautiful reimagining of the universe lies a subtle but crucial detail, a potential fissure in the absolute barrier of light speed. While special relativity establishes that nothing can move times through time-space faster than light, general relativity unveils a different truth altogether. Space-time itself is a dynamic and active entity. It is not static, but can stretch, compress, and even ripple much like the surface of a pond. And we have, in fact, directly observed these ripples. In 2015, the scientists at the LIGO Scientific Collaboration made history by detecting gravitational waves' minuscule distortions in space-time generated by the cataclysmic collision of two distant black holes. But the universe vibrates on an even grander scale. The entire cosmos is in a state of constant expansion. During a brief, explosive period in the early universe known as inflation, the fabric of space itself expanded at a truly incomprehensible rate. Regions that were once infinitesimally close were flung apart from each other faster than a beam of light could have traveled between them. This seemingly paradoxical event does not violate relativity because no particle or object locally broke the cosmic speed limit. It was not a race through space, but rather the expansion of space itself, carrying everything along with it. A simple analogy helps to visualize this concept. Imagine drawing two dots on the surface of an uninflated balloon. As you inflate it, the distance between the dots increases, not because the dots are crawling across the rubber, but because the surface itself is stretching. From the perspective of an ant standing on one dot, the other dot could recede at a speed far greater than the ant could ever hope to crawl. This is not because the ant has broken its own speed limit, but because the very ground beneath its feet is expanding. This is precisely what we observe in our own universe today. The expansion continues, and when we look at very distant galaxies, we see them receding from us at effective speeds greater than that of light. This is possible only because the vast expanse of space between us and them is continuously stretching. The universal speed limit, it turns out, applies to an object's motion times through times its local patch of space. It does not, however, apply to the expansion times of time-space itself. This distinction may appear to be a subtle, almost semantic point, but its implications are profound, completely altering the landscape of what might be possible. If the fabric of space can expand and contract, then distance is not an immutable, fixed quantity. It is elastic. And if distance is elastic, then perhaps interstellar travel is not merely a problem of propulsion, but one of geometry. Consider the challenge of crossing a vast ocean. One approach is to build a faster and more powerful ship, battling the waves and pushing harder against resistance. This mirrors conventional space propulsion, which attempts to push a vessel harder through a fixed distance. But what if there were another way entirely? What if, instead of building a faster ship, you could somehow shrink the ocean itself, drawing the distant shore closer while the water behind you expanded away? The journey would become dramatically shorter, not because your vessel moved any faster, but because the path itself was fundamentally altered. This is the crucial conceptual leap that has reshaped the entire conversation around faster-than-light travel. The mathematical language describing this relationship is found in Einstein's field equations. These equations elegantly detail how a given distribution of mass and energy curves the surrounding spacetime. Crucially, however, they do not forbid the existence of exotic or unusual shapes of spacetime. For decades, physicists approached these equations from one direction. They would start with a known distribution of matter, such as a star, and then calculate the resulting curvature. This method successfully predicted phenomena like black holes and gravitational waves, but mathematically, the equations work both ways. Instead of asking what curvature a certain type of matter creates, one could pose a more speculative question. What kind of matter or energy would be required to create a specific desired curvature? This reversal of the problem opens a fascinating door. What if we were to begin with a desired geometry, for instance, a self-contained bubble of flat space-time, and then use the equations to determine the energy needed to generate it? This question would lie dormant for much of the 20th century, but its theoretical foundation was laid the moment Einstein revealed that space-time was not merely a passive background. To truly grasp why this matters, we must return to the core idea that space-time is a dynamic architecture. In special relativity, all motion is relative. There is no absolute frame of rest. Yet, the geometry of space-time provides an underlying structure, defining how we measure distances and durations. If that fundamental geometry can be changed, then our very definition of what constitutes distance must also change. Imagine a spacecraft setting out on a journey to a star 10 light-years away. Normally, this means traversing 10 light-years of space, a voyage that would take at least a decade at light speed. But what if the space in front of the ship could be compressed, effectively shrinking that 10 light-year expanse? From the perspective of an observer on Earth, the ship might appear to arrive in less than 10 years, seemingly violating the cosmic speed limit. For the crew inside the vessel, however, their ship may never have traveled faster than light relative to its immediate local surroundings. This concept is not about achieving greater speed in the conventional sense. It is about reshaping the very ruler by which we measure the journey. And astonishingly, Einstein's equations do not explicitly prohibit such a reshaping. The essential insight is this: the geometry of space-time dictates which paths are possible. If you can change the geometry, you can change the available paths. In the perfectly flat space of simple geometry, the shortest distance between 2 points is a straight line. But in a curved space, that shortest path also bends. On the surface of a sphere, for example, a path that feels perfectly straight locally is actually part of a great, curving circle on a global scale. General relativity simply extends this fundamental principle into the 4 dimensions of spacetime. The universe, it suggests, is not a fixed and rigid grid. It is a malleable, pliable medium, and it is within this very malleability that the most extraordinary possibilities may reside. Once we accept that space-time is not a fixed stage but a malleable fabric, a concept of revolutionary potential emerges. What if, instead of contending with the immense energies required to approach the cosmic speed limit, we could bypass the problem altogether? Imagine a vessel that remains stationary in its own local pocket of space, while the geometry of space-time itself performs the traveling. The concept is analogous to standing on a moving walkway. You are at rest, yet the surface beneath you carries you toward your destination. Or consider a surfer, lifted and propelled by a powerful ocean wave, who has no need to swim faster than the water itself. The wave is what moves, and the surfer simply rides along within its form. This approach circumvents the prohibitions of special relativity, as nothing within this bubble ever exceeds the speed of light relative to its immediate surroundings. The motion is fundamentally embedded within the geometry of space-time. If the universe itself was capable of expanding faster than light during its inflationary epoch, it poses a profound question. Could a localized distortion of geometry accomplish a similar feat? The mathematics suggested that it could, a suggestion that would soon be given a concrete foundation. In 1994, the theoretical physicist Miguel Alcubierre gave this possibility a precise mathematical articulation. He reframed the fundamental question from how can we push a spacecraft faster to how can we move space-time itself. His work focused not on designing a new kind of engine, but on designing a new kind of space-time geometry. Employing the framework of Einstein's general relativity, Alcubierre formulated a solution describing a bubble of calm, flat space-time. This tranquil interior would be enclosed by a surrounding wave of intense distortion. In front of the bubble, space-time would be compressed. Behind it, space-time would expand. The flat region inside would be carried along on this traveling wave. A ship contained within this pocket would experience no acceleration, no crushing g-forces, and no extreme time dilation. For the crew, the journey would be perfectly serene, as if they were simply floating in deep space. From an external observer's perspective, however, the entire bubble could be seen traversing the cosmos, potentially at speeds far greater than that of light. The profundity of this concept can be grasped by picturing a taut sheet of fabric. If you were to generate a small ripple that travels across its surface, an object like a coin placed upon that ripple would not be sliding across the fabric. It is simply carried along by the wave's motion. The coin remains locally still, while the wave itself moves. The Alcubierre warp bubble functions on a similar principle. A spacecraft would rest inside an undisturbed pocket of space-time while the surrounding distortion propagates, carrying the pocket along with it. A critical point is that no object inside the bubble breaks the light-speed barrier relative to its immediate vicinity. The universal speed limit is respected at every local point. Nevertheless, the bubble as a whole could cross vast interstellar distances in a tiny fraction of the time light would take to travel through normal, undistorted space. This is not a loophole in special relativity. It is a direct application of general relativity. While special relativity forbids faster than light travel times through time-space-time, general relativity permits space-time itself to bend, stretch, and move. Alcubierre's genius was in recognizing how these two truths could coexist. Another analogy helps visualize the idea. Imagine two cities separated by 1,000 kilometers of land. The conventional method of travel is to drive across that distance. But what if the land itself could be folded like a page in a book, bringing the two cities adjacent to one another? You could simply step across the gap, and upon unfolding the page, find you had arrived at your destination without ever moving faster than a walking pace relative to the ground beneath your feet. The warp drive is the geometric equivalent of this folded page. It is not a literal folding, but a dynamic compression and expansion of the space-time fabric. Ahead of the bubble, space-time contracts, effectively reducing the distance to the destination. Simultaneously, behind the bubble, space-time expands, pushing the point of origin further away. The result is a net translation through space, accomplished without any traditional form of motion. The Alcubierre metric provides a precise mathematical description of this phenomenon. A localized area of flat spacetime contained within a shell of extreme curvature. The velocity of the bubble is determined by the gradient of this curvature. A steeper gradient corresponds to a higher effective speed. In principle, the equations impose no upper limit on this velocity. It could be 10 times the speed of light, or 100 times, or even more. This allows for a startling scenario. From the perspective of an observer on Earth, a voyage to a star 10 light-years away could be completed in mere weeks. Yet for the crew inside the bubble, time would pass normally, with no relativistic effects such as slowed clocks or suspended aging. It sounds almost like a cheat code for the universe, but the mathematics is rigorous. Alcubierre did not rely on approximations. He presented an exact solution to Einstein's field equations. This fact sent shockwaves through the physics community. For decades, faster-than-light travel had been dismissed as a fundamental violation of relativity. Suddenly, the theory of relativity itself appeared to provide a pathway, at least on paper. The proposal was met with a firestorm of both excitement and profound caution. While the equations answered one profound question, they immediately raised several more daunting ones. How could such a bubble be generated in the first place? What kind of energy source could possibly create this specific curvature? Could such a structure even remain stable during its journey? And perhaps the most unsettling question of all, what would this capability imply for the fundamental principle of causality? These are not trivial details, but are instead hurdles that challenge the very foundations of physics. The first challenge to confront was a conceptual one, rooted in the core of general relativity. Within the framework of general relativity, spacetime curvature is a direct result of the distribution of mass and energy. Stars bend spacetime with their immense gravity, as do planets on a smaller scale. Even light itself contributes to this curvature. It follows, therefore, that if you wish to create a specific, desired shape in spacetime, such as the Alcubierre bubble, you must arrange mass and energy in a very particular configuration. The next logical step for Alcubierre was to work backward from his solution. Given this ideal bubble geometry, what kind of stress-energy tensor, the mathematical object that describes the distribution of matter and energy, would be required to produce it? It was here that the idea's sheer elegance encountered the unyielding realities of physical law. The calculations uncovered a startling requirement. Creating the warp bubble would necessitate regions of negative energy density. This does not simply mean an area with less energy than its surroundings. It means a region with less energy than a perfect vacuum, an energy state below absolute zero. To understand why this is necessary, we must recall what the bubble geometry demands. Space-time must contract in the front and expand in the back. The geometry requires space-time to defocus light rays in some areas and focus them in others. Ordinary matter and energy always curve space-time. In one way, it pulls inward, it focuses trajectories, it attracts. This is the gravity with which we are familiar. To generate the outward-pushing, repulsive curvature needed for the expanding part of the bubble, the equations call for something truly exotic: matter or energy that gravitates repulsively. In the realm of quantum physics, minuscule negative energy effects are known to exist. The Casimir effect, for example, demonstrates that vacuum fluctuations between two parallel plates can create a tiny pocket of negative energy density. But these effects are incredibly small and transient. The Alcubierre drive, in contrast, would require vast, stable quantities of this negative energy. This one requirement continues to be the most formidable barrier, separating a beautiful mathematical concept from a potential physical reality. The initial calculations for powering a warp drive were nothing short of breathtaking, suggesting an energy requirement equal to the mass of the entire known universe, while subsequent refinements have drastically lowered this figure, first to the mass of a star, then to a planet, and in some highly speculative models, even less. The sheer scale of the demand remains profoundly beyond our grasp. This isn't merely an engineering problem to be solved with better technology. It raises a fundamental question of physics. Can such an immense concentration of energy, in the precise configuration needed, even exist? Yet, this is only the first of many barriers. A deeper complication is woven into the very fabric of the drive's geometry, a paradox involving its horizons. A warp bubble traveling faster than light would effectively create a boundary, sealing its interior off from the universe outside. Any signals sent from within could never reach the bubble's leading edge, because the front of the bubble would be receding from the ship at superluminal speeds. As a result, the crew would be passengers without control, unable to communicate with the spacetime they are approaching. This means they could not steer, apply brakes, or make any mid-course corrections. The very geometry that grants faster than light travel appears to take away any ability to direct it. Then there is the daunting matter of arrival. As the bubble traverses the cosmos, it would inevitably interact with the sparse particles and radiation of interstellar space. Some theoretical models indicate that these particles could accumulate at the bubble's forward boundary, becoming intensely compressed by the contracting spacetime. When the drive is disengaged and the bubble collapses, all of that stored energy could be unleashed in a single, devastating burst, potentially annihilating anything at the destination. Other analyses propose a different, though equally perilous, outcome. They suggest that a buildup of radiation near the bubble's edge could render the entire structure unstable. Quantum effects at this horizon might even trigger intense particle creation, a phenomenon reminiscent of the Hawking radiation that emanates from black holes. The more physicists scrutinized the concept, the more intricate and challenging it became. The Alcubierre warp drive is not explicitly forbidden by Einstein's equations. However, those foundational equations do not represent the complete picture of reality. General relativity is a classical theory, a grand-scale description of gravity, but it does not incorporate the strange and subtle rules of quantum mechanics. When these quantum effects are factored in, a new set of constraints immediately comes into play. Principles known as quantum inequalities, for instance, place strict limits on how much negative energy can be concentrated in one place and for how long it can persist. Furthermore, stability analyses have revealed that the bubble's delicate curvature could be extraordinarily fragile, amplifying even the tiniest quantum fluctuations into a catastrophic collapse. The warp bubble, it turns out, might be mathematically sound, but physically untenable. And yet, despite these seemingly insurmountable obstacles, the idea remains one of the most profound insights to emerge from theoretical physics in the late 20th century. Its true value was not in providing a blueprint for a starship, but in revealing something extraordinary about the cosmos itself. The cosmic speed limit, we learned, is not a simple prohibition. It is a deeply layered defense. While nothing can locally outrun a beam of light, the fabric of space-time itself can be shifted on a global scale. But every theoretical attempt to exploit this flexibility runs into deeper principles, energy conditions, quantum constraints, and the preservation of causality. In this sense, the Alcubierre metric did not provide a path to the stars. It provided a mirror. It showed us that the structure of reality is far richer and more intricately constrained than either simple optimism or pessimism could ever predict. The mathematics unlocked a door, only for the universe to stand behind it, reminding us that what is permitted on paper is not always permitted in practice. When Miguel Alcubierre first completed the mathematics for his warp bubble, the initial excitement was quickly tempered by the next, inevitable calculation. Einstein's equations are not just about geometry. They inextricably link that geometry to the presence of matter and energy. Space-time bends only because something is there to bend it. Every contour in the cosmic fabric must be paid for with a corresponding source. Alcubierre was thus forced to ask the critical question: what kind of energy distribution could possibly create this moving bubble of space-time? The answer was not merely inconvenient, it was a shock to the foundations of physics. The warp bubble required something called negative energy density, not a low amount of energy, or zero energy, but an energy state below the absolute vacuum of empty space. To appreciate why this is so significant, one can imagine gravity as a force that generates an inward curvature, pulling things together. All ordinary matter and energy, from a speck of dust to a galaxy, produces this kind of inward curve. It is the reason why gravity is an attractive force, focusing the paths of objects and drawing them toward one another. The warp bubble, however, demands the opposite. To function, it requires space to contract sharply in front of it and expand rapidly behind it. This specific geometry necessitates regions where space-time curves outward, defocusing pathways rather than concentrating them. Ordinary matter simply cannot do this. Its gravitational influence always pulls inward. The equations were unambiguous. Only a substance with negative energy density could produce the required repulsive, outward-pushing gravitational effect. And negative energy is not a material that can be mined or refined. Quantum theory does offer fleeting, microscopic glimpses of this exotic phenomenon. In what is known as the Casimir effect, two uncharged metal plates placed incredibly close together can alter the quantum fluctuations of the vacuum between them. This creates a minuscule region where the energy density dips slightly below that of the surrounding empty space. However, these quantum effects are incredibly small, highly localized, and extremely short-lived. The original warp drive proposal suggested an energy requirement equivalent to the mass energy of an entire star. Even though later refinements have lowered this to the mass of a planet or less, the need for even a single kilogram of stable negative energy would represent a leap into a realm of physics currently unknown to us. Worse still, the laws of quantum field theory impose strict regulations known as quantum inequalities. These principles effectively state that negative energy cannot be accumulated freely. If it does appear, it must be balanced by a greater amount of positive energy nearby. The more negative energy one attempts to concentrate, the shorter the duration it is permitted to exist. It is as though the universe allows one to take out a loan against the vacuum, but the terms are severe. The loan must be small, paid back almost instantly, and always with interest. The warp drive, by contrast, demands a sustained, macroscopic region of negative energy, arranged with impossible precision. Nature, it seems, is simply unwilling to grant such a request. But let us imagine for a moment that this fundamental obstacle could be overcome. Suppose some future breakthrough in physics unlocked a source of stable, usable, negative energy. Would the path to a functional warp drive then be clear? As scientists looked deeper, they realized the answer was not so simple. Even if the negative energy problem were solved, the warp bubble's geometry introduces a nothe. Any signal originating from within the spacecraft, even one directed toward the bubble's leading edge, would be fundamentally unable to ever reach it. This limitation presents a profound and fundamental problem for any potential crew. Without the ability to send instructions or information to the boundary of the bubble, they would have no way to steer their vessel, adjust its shape, or even initiate a slowdown. They would be effectively sealed inside a self-contained pocket of space-time, completely isolated from the very geometry that propels them forward. The feature that makes faster-than-light travel possible, the principle of causal separation, is also precisely what renders it uncontrollable from within. The situation is akin to being a passenger on a train that, once launched, cannot be stopped, slowed, or redirected by anyone on board. The challenge of stopping is, upon reflection, equally perplexing. In order to safely collapse the warp bubble at a destination, some form of external influence must alter the space-time curvature ahead of the ship. Yet from inside the bubble, that crucial region is forever beyond reach. One speculative solution imagines a network of infrastructure waiting at the destination to manage the arrival, but this merely shifts the impossibility. How would such a network ever be constructed and coordinated across vast interstellar space if communication itself is bound by the speed of light. Beyond the paradox of control lies the equally critical question of the bubble's fundamental stability. The specific geometry of a warp drive is known to be exceptionally delicate, demanding the creation of extreme gradients of curvature at its boundary. In certain important mathematical ways, these boundary regions are not unlike the event horizons of black holes. According to the principles of quantum field theory, such intense curvature can provoke the creation of particles directly from the vacuum of space, a phenomenon closely related to Hawking radiation. In the specific context of a warp bubble, detailed calculations indicate that this process could generate an intense field of radiation that accumulates near the boundary. This flood of high energy might then destabilize the bubble, draining its power or even causing the entire configuration to disintegrate. This raises a fascinating question. Could the very act of shaping spacetime so dramatically ignite quantum effects powerful enough to tear that same structure apart? Even if a bubble could somehow be stabilized against such quantum effects, there remains the problem of its interaction with the interstellar medium. The vast void between stars is not truly empty. It is a sparse but persistent sea of drifting particles, from individual atoms and microscopic dust, grains to high-energy cosmic rays. A warp bubble moving at superluminal speeds through this medium would inevitably encounter these particles. Some theoretical models predict they would be swept up and amassed at the front boundary, dangerously compressed by the contracting space ahead of the ship. Over the course of a long interstellar journey, the energy accumulated from these countless impacts could become immense. Upon arrival, the collapse of the bubble could then unleash this stored energy in a devastating burst of radiation, potentially powerful enough to sterilize an entire planetary system. In this sobering scenario, a successful voyage could end with a catastrophe of unimaginable scale. With each layer of analysis, another formidable constraint seems to emerge. The negative energy required for the original concept may not exist in sufficient quantities. Even if it does, controlling the bubble from within appears to be a logical impossibility. If control were somehow solved, its fundamental stability would remain deeply uncertain, and if stability could be assured, the interactions with interstellar matter present a lethal risk upon arrival. Yet, woven through all these physical challenges is the deepest concern of all: causality. Faster-than-light travel between distant locations allows for the creation of what are known as closed time-like curves, paths through spacetime that loop back to their own past. In certain frames of reference, a superluminal round trip could enable a traveler to arrive back home before they even departed. This is not merely a philosophical inconvenience. It represents a fracture in the logical structure of physics, where cause must always precede effect. Some theorists speculate that a future theory of quantum gravity may include a principle of chronology protection, where the universe itself actively prevents such paradoxes. If true, any warp bubble threatening causality might be automatically destabilized by quantum effects, a cosmic safeguard to protect its own logical consistency. The pattern that develops from this line of inquiry is unmistakable. While the warp drive is a valid solution within the mathematics of general relativity, each attempt to ground it in physical reality reveals deeper layers of constraints. It is like digging through one layer of impenetrable bedrock only to discover another, even harder, layer beneath it. The speed of light is not protected by a single barrier, but by an interlocking system of cosmic principles: energy conditions, quantum stability, causal structure, and geometric consistency. Each of these principles reinforces the others, so that if one were somehow overcome, another would immediately stand in its place. The dream of faster-than-light travel remains one of the most powerful ideas in the human imagination. But the deeper we explore the equations, the more the universe appears to whisper the same quiet message. You may imagine this, you may calculate it, and you may even write it into the language of space-time. Bringing it into physical existence, however, is another matter entirely. For many years, the exotic matter problem was seen as the single, fatal flaw in the warp drive concept. The logic was straightforward. If negative energy is essential for the drive to function, and it cannot be produced in the necessary amounts, then the entire idea collapses. This led physicists to ask a different, more creative question. What if the issue was not the geometry itself, but rather the type of energy we assumed was needed to create it? In recent years, several theoretical proposals have emerged that attempt to redesign warp-like configurations of space-time using only positive energy, the ordinary kind that fills our universe. No exotic matter and no negative energy density would be required, just clever arrangements of space-time curvature. At first glance, this sounds like a revolutionary breakthrough. If the primary obstacle could be removed, perhaps the remaining challenges would become manageable. But as always, the deeper one ventures into the equations, the more subtle the story becomes. Some of these new solutions describe what are known as subluminal warp configurations. They are capable of producing localized distortions in space-time that mimic a warp bubble, with a contraction in one region and an expansion in another. However, their overall motion remains steadfastly below the speed of light. In these models, the energy conditions of general relativity can be satisfied without needing to invoke any negative energy. The mathematics is clean and the geometry is elegant, but there is a crucial distinction. A subluminal warp bubble does not sever the causal connection between its interior and the outside universe. Signals can still pass between them, which means the bubble can be influenced and controlled from within. It behaves more like a moving, self-contained gravitational wave than a true faster-than-light vessel. And because it never exceeds light speed, it does not bypass the fundamental barrier imposed by special relativity. It may offer a novel means of propulsion, but it does not deliver on the promise of superluminal travel. Other, more ambitious proposals go even further. They endeavor to design constant velocity warp geometries that could mathematically permit superluminal motion while using only positive energy distributions. The resulting headlines can be dramatic, often proclaiming that scientists have removed the need for exotic matter entirely. Yet, as promising as this sounds, there is a critical catch hidden deep within the mathematics. A great number of these proposed solutions share a perplexing quality. They describe eternal geometries, configurations that must have always existed. They cannot be built from a flat region of space-time using any known physical process. This means they cannot be switched on or off, nor can they accelerate or decelerate. It is as if we discovered a flawless tunnel bored through two distant mountains, only to find it was a natural formation, impossible to build, alter, or even access from the outside. The mathematics may be valid, but the underlying physics remains unreachable. Then, we encounter the challenge of acceleration. The journey from subluminal to superluminal speeds is not a smooth continuum. As a warp bubble approaches the speed of light, its underlying geometry undergoes a fundamental change. Horizons begin to form, creating a causal separation that isolates the interior of the bubble from the universe outside. This is not like pressing harder on an accelerator. It is more akin to a phase transition, like ice melting into water. The physics that governs one state does not simply extend into the next. When this threshold is analyzed, physicists find that the energy demands spike to astronomical levels. Even designs that rely solely on positive energy below light speed suddenly reintroduce the need for exotic matter to cross into the superluminal realm. The wall simply reappears, albeit in a different guise. There are also attempts to leverage the complex, non-linear nature of Einstein's equations. General relativity is not a simple, linear theory. In it, gravitational fields interact with themselves. Energy curves spacetime, and in turn, curved spacetime dictates the flow of energy. This intricate dance creates possibilities for clever arrangements. Perhaps a precise configuration of multiple positive energy distortions could work in concert, collectively mimicking the effect that negative energy would otherwise be required to produce. In mathematics, indirect methods sometimes achieve what direct approaches cannot. However, detailed investigations consistently run into what are known as focusing theorems, profound principles within general relativity that dictate how positive energy must behave. Positive energy invariably focuses geodesics, pulling the trajectories of light and matter inward and strengthening their convergence. A warp bubble, by its very nature, requires the exact opposite in key regions, a defocusing effect, where space-time spreads outward rather than contracting. These focusing theorems are not superficial guidelines. They are direct consequences of the core structure of the equations. Attempting to compel positive energy to behave like negative energy is akin to trying to make gravity repel without fundamentally altering the nature of gravity itself. The geometry simply resists such manipulation. Other proposals venture into the realm of modified gravity, suggesting slight alterations to Einstein's equations. These alternatives are often inspired by efforts to explain cosmic mysteries like dark energy or the accelerating expansion of the universe. Within some of these theoretical frameworks, warp-like solutions do appear to be more easily constructed, but this convenience comes at a steep price. General relativity has withstood every experimental test ever devised, from the subtle precession of Mercury's orbit to the direct detection of gravitational waves. Any modification must flawlessly reproduce all of these verified successes. The problem is, most modifications that permit easier warp geometries also predict subtle deviations from general relativity in other areas, deviations that have never been observed. The more carefully a modified theory is calibrated to align with experimental data, the more it begins to resemble standard general relativity, and the closer it gets, the less of an advantage it offers for constructing a warp drive. Once again, the promising loophole begins to narrow until it all but disappears. Another avenue of research explores soliton-like solutions. In other fields of physics, solitons are stable, self-sustaining waves that propagate without losing their shape, behaving almost like particles. The hope is that space-time itself could host a similar distortion, a stable, solitary wave with a flat interior that could function as a warp bubble without exotic matter. While mathematically, some of these soliton solutions do exist and are stable against small disturbances, they fall prey to the same limitation as their constant velocity counterparts. They cannot be generated from ordinary spacetime through physically plausible means. The equations permit them as eternal, pre-existing features of the universe, not as engineered vehicles we can build. Even more concerning is the fundamental issue of stability. Warp geometries, particularly those capable of superluminal travel, appear to be profoundly unstable when exposed to quantum fluctuations. The boundary of the bubble represents a region of extreme curvature, and even the tiniest quantum disturbances at this frontier could be amplified exponentially. This could cause an uncontrollable accumulation of radiation, instantly destroying the bubble. It is like trying to balance a pencil perfectly on its sharpest point. While the laws of physics theoretically allow for a state of perfect balance, in practice, the slightest vibration will cause it to topple. A warp bubble may be that pencil, balanced precariously on a peak of space-time curvature, where the quantum world itself ensures its collapse. This leads to an even deeper concept known as the chronology protection conjecture, an idea put forth by Stephen Hawking. This conjecture posits that the fundamental laws of physics are structured to prevent the formation of closed, time-like curves, pathways, through space-time that would permit travel into one's own past. Because superluminal warp drives could, with a clever arrangement of trips, create such paradoxical loops, they pose a direct threat to causality. If chronology protection is a genuine principle of the universe, then any attempt to construct a superluminal warp bubble might automatically trigger overwhelming quantum instabilities. The universe wouldn't just forbid faster than light travel. It might actively destabilize any geometry that even attempts to make it possible. Each new proposal, each failed attempt, teaches us something invaluable about the universe. It reveals just how tightly woven the principles of physics truly are. Energy conditions are inextricably linked to stability. Stability is connected to the uncertainties of quantum fluctuations. Quantum fluctuations are tied to causality, and causality circles all the way back to the ultimate speed limit of light. This is not a single, simple wall blocking our path. It is an intricate network of beams and supports holding up the entire structure of space-time. If you manage to remove one, the others merely shift to hold the limit firmly in place. So when we hear that scientists have proposed a new way to travel faster than light, the statement is not false. The mathematical proposals are real, the equations are often valid, and the creativity behind them is genuine. But each new design does not dismantle the barrier. Instead, it serves to reveal just how deeply that barrier is embedded within the very architecture of reality. The speed of light is not a limit enforced by a single law. It appears to be enforced by the total consistency of all the laws working together. After decades of brilliant equations, theoretical refinements, and bold proposals, we are left with a strange and profound conclusion. Faster-than-light travel is not forbidden by any single edict in the book of physics. In the abstract realm of mathematics, it is even permitted. Yet it seems the universe itself conspires to keep it forever a dream. While the mathematics of warp travel seems to grant us permission, every effort to translate this permission into a physical reality has been met with profound resistance. It is this consistent pattern of opposition that represents the true discovery. When physicists first began to investigate warp geometries, it was as if they had found a secret passage within Einstein's theories. The equations themselves did not forbid such a concept. In fact, they quietly allowed for it, presenting an elegant and exact solution. But a curious thing happened the moment this geometry was asked to conform to physical laws. The universe, it seems, actively pushed back. The need for negative energy arises, yet quantum theory places strict limits on its existence. Alternative designs using only positive energy are conceived, but they prove impossible to either create or steer. Even when stable configurations are proposed on paper, they appear vulnerable to being torn apart by quantum fluctuations. While causality is preserved on a local scale, paradoxes threaten to emerge across the entire cosmos. The challenge is not a single, isolated obstacle. Instead, the obstacles are interlocked, each one reinforcing the others. This is not the signature of a temporary engineering problem waiting for a breakthrough. It is the clear behavior of a fundamental, structural limit. Consider the effort to remove a single support pillar from a vast, ancient cathedral. One might begin by chipping away at a single stone, only to discover the immense weight of the roof it supports. If the pillar were removed entirely, arches would buckle and walls would crack. The entire structure would fail, not because of one flawed component, but because every piece is fundamentally dependent on every other. The speed of light appears to be just such a foundational pillar in the architecture of reality. It is inextricably linked to causality, which governs the sequence of events. It is tied to energy conditions, which dictate how matter and energy can shape spacetime. It connects to quantum stability, influencing how the vacuum behaves in regions of extreme curvature. To remove it would not be to simply bend a rule, but to begin to unravel the very fabric of the cosmos. This interconnectedness reveals something deep about the nature of physical law. The universe is not governed by a loose collection of independent statutes, but by a tightly woven tapestry. If you pull on a single thread, you feel tension propagate across the entire fabric. In this sense, the various proposals for a warp drive have served as a kind of stress test. probing the deepest structure of spacetime by asking, what if we push here? The response from the universe is always the same, a resistance that is not arbitrary, but deeply principled. There is a philosophical lesson to be drawn from this. Throughout history, mathematics has often outpaced physical experimentation. The equations of electromagnetism predicted the existence of radio waves long before they were ever detected. The mathematics of quantum theory foresaw antimatter before it was observed in a lab. In those instances, a mathematical possibility was a direct preview of a physical discovery. The elegant geometry of warp drive theory naturally tempts us to believe we are in a similar moment, that an exotic solution today will become an engineering reality tomorrow. However, the difference is both subtle and crucial. In those earlier scientific revolutions, the new mathematics did not fundamentally conflict with deeper, already established principles. Instead, it revealed new phenomena that fit harmoniously within the existing structure of physics. Warp drives, in stark contrast, seem to strain against multiple foundational principles all at once. They challenge our understanding of energy conditions, of quantum stability, and of causal consistency. And every time physicists devise a clever way to relieve one of these tensions, another one almost inevitably tightens. It is as if the universe guards its ultimate speed limit, not with a single, simple lock, but with an intricate system of interlocking mechanisms. Yet, this exploration is far from meaningless. On the contrary, by attempting to break this cosmic limit, physicists have uncovered just how deeply it is embedded in the nature of reality. These very thought experiments have exposed profound connections between general relativity and quantum theory that might have otherwise remained hidden in plain sight. They have clarified why causality is not merely a convenient assumption, but a structural necessity for a coherent universe. In this way, the apparent impossibility of the goal has taught us as much as its achievement ever could. This story also imparts a certain humility. Human history is a long chronicle of supposedly insurmountable barriers being overcome. We navigated vast oceans once thought to be impassable. We took to the skies, which were once considered sacred and unreachable. We unlocked the power of the atom and even set foot on the moon. It is natural, then, to assume that every limit is merely temporary, a challenge awaiting a more advanced technology. But the speed of light may prove to be different. It may not be a technological barrier at all, but rather a fundamental reflection of what the universe times is asterisk. A universe where causality consistently flows in a single direction. A universe where the geometry of space-time adheres to strict relationships with energy. A universe where stability is maintained by constraints that protect its very coherence. Perhaps that same coherence is what allows for the emergence of complexity for stars, planets, chemistry, and ultimately, life itself. If space-time could be easily manipulated, if the order of cause and effect were flexible, and if energy conditions could be casually violated, the universe might not be a stable enough stage for existence to unfold. The very same rigidity that frustrates our dreams of interstellar travel may be the rigidity that allows atoms to form and galaxies to endure for billions of years. From this vantage point, the cosmic speed limit is not merely a prison wall confining us. It is part of the essential framework that makes a comprehensible reality possible. We are not trapped by a cruel rule. We are supported by a consistent and magnificent structure. And still, the wonder remains. The fact that Einstein's equations even contain the ghost of such possibilities is itself astonishing. The mathematics itself hints at a reality far more flexible, dynamic, and subtle than classical physics ever imagined. But this flexibility does not imply lawlessness. The river of space-time can bend and curve. It can ripple and expand, but its fundamental current, the propagation of causality at the speed of light, always remains constant. Perhaps the deepest insight is this: the universe permits imagination. It allows for theoretical exploration, and it invites us to stretch its mathematical laws to their absolute limits. It does not, however, promise that every mathematical door will open into physical reality. Some of these doors, it turns out, lead not to new corridors of travel, but to new corridors of understanding. The pursuit of a warp drive has not, in fact, brought us physically closer to the stars, as science fiction once promised, but it has brought us intellectually closer to understanding why they must remain distant. And that understanding is certainly not a defeat. It is a profound and welcome clarity. The speed of light still stands, not as a challenge waiting to be conquered, but as a cornerstone of a universe whose structure is deeper and more beautifully interconnected than we ever knew. Here at Calm Space, we find that this journey into deeper understanding is one truly worth taking.